important word in the title, which is introduction. This won't be a very comprehensive course. What I want to go through during this series of 4 courses is the very basic concepts of CUDA, and then towards the end also a little bit more things on how to make it work as fast as you can. But the first goal, if there are basically 2 goals in this course. The first one is, of course, as usual, to write correct programs. So programs that compile, that run without errors, and that produce the expected output. And making them fast is only the second goal. We will see that later. So perhaps before I start really going into the topic, I should tell you a little story about some computation I was struggling with about 3 years ago. It was about solving a Boltzmann equation with a deterministic method. So the method where you really compute the collision integrals that are in the right-hand side of the equation. And this is really the computationally intensive part of solving the equation. And this was during the summer, so it meant I could use a large fraction of the cluster we have here, Kanta, and I managed to get 32 nodes of Kanta out of, so that's almost half of the machine. And one run took me 2 weeks to complete with half of the machine. So then I realized this was not going to work for practical purposes, because if I wanted to do physics with this program, I would have needed to do a few tens of runs, and I will never have the conditions again where I could get this fraction of the machine. And then I started looking into CUDA, because it was also announced by Laurent around that time that we had actually a machine in the lab with 2 GPUs for playing with. So I started looking into that, and it was actually hugely beneficial for this particular code. Instead of taking 2 weeks on cluster, it was running in a few hours on this machine, a couple of hours typically. So this is lecture 1. Here is the outline, but of the full course. So the items I will go through during the first lecture are those in green here. So it's mostly an introduction, and in the last part I will have one example that I will discuss in detail to explain how a typical CUDA computation is organized. So I will first go through discussing what's a GPU, what's inside, what kind of tasks they are good at. They are not good at certain things and very good at others. And then we will go in detail through this first example. And I will, so it's a very basic example. It takes 10 lines of code roughly. And I will have a couple of iterations on that to try to improve it. And these are the outlines of the second, third, and last lecture. But this is not for today. So let me start by an introduction. This is a slide I took from Grégoire. It shows the evolution of CPUs, not GPUs, CPUs, over the last 50 years, roughly. Starting from the 1970s, and there are various measures of quantitative measures of what's inside CPUs of that time. And you see that, for instance, if you look, the blue dots, they measure the performance of a single computing core. And its evolution with time, and you see that it's kind of reaching a plateau in the last 10-15 years. It's not growing very fast now compared to what it was doing 30 years ago. And this is compensated by another evolution of CPUs, which is that since we cannot increase the performance of one core, we will increase the number of cores. And now you see that the number of cores in very high-end CPUs is reaching a number of the order of 100, sometimes a little more. And the main reason why the performance of a single core cannot increase ad infinitum is basically the typical thermal power they release and the difficulty in just getting rid of this heat. And you see that for the last 20 years almost, the typical power is reaching a plateau of around a couple hundred watts typically. This varies depending on the models, but the very high-end CPUs typically need to dissipate 300 watts of thermal power. And given the size of the package they are built from, there is a certain limit to the power you can dissipate realistically. So this cannot grow very much more. And if the typical power is limited, the only way to make a core faster, you cannot increase its frequency because the power it outputs goes, I think, like the square of the frequency. So if you want to increase the frequency, you have to make it shrink in size also. All the transistors have to become smaller because the output power is also going like the size of the transistors. But now it's reaching a certain limit as well because the latest CPUs typically have the finer details they contain are I think 4 nanometers, and it's getting close to the size of one atom, and it's not going to decrease much further. So nowadays, I will say the main gain in computing power for a CPU is by increasing the number of cores, which means that the number of transistors they contain also is linearly increasing. So a typical CPU, this is a kind of a sketch of how a typical CPU is organized. It can have one or two, these are for cheap CPUs, two of the order of 100 cores. These are not very common. These cores share the main memory of the computer. They see the same memory in general. And they usually share some of the cache levels as well. A CPU is a very generic computing device, which means that in particular, if you have several threads of execution, so think of different processes, for instance, they can perform totally unrelated tasks. The logic, there is a part of the CPU which is organizing which computation is done at every moment. And this logic circuitry is such that it can run arbitrarily different tasks on different threads. And then how this computing power is shared among the processes is handled by the operating system, which knows which processes need to run, and it hands a certain time slice of a given core or a few cores to one particular thread. And the parallel programming on this type of CPUs is done very often with something which is called OpenMP, which is a way to decorate an existing program to tell it that a certain loop, for instance, can be split into various threads that will execute on various cores. And in a sense, the parallel programming for a generic CPU like that is, as you will see, sometimes more challenging than the parallel programming for a GPU, because of this possibility that each thread is doing totally different things. And then it means that you have to, if you have dependent tasks, for instance, that are executed by different threads, it's your responsibility, the person who programs who write the program to make sure that they do things in the order you expect if there is a certain relationship between these different tasks. On a GPU, in a sense, this is simpler because the hardware provided by a GPU is more restricted, and most of the time it forces all the threads to run exactly the same instruction at the same time. So in a sense, all this thinking about which tasks are dependent or not is void and done for you because you don't have this option. So now let me have the same type of description for what's in a GPU. So GPU is the name means Graphical Processing Unit. Because originally, of course, GPUs came from the video game industry, and they were designed to handle the compute-intensive parts of generating graphics. And the idea was that every pixel in an image is independent of the others, so generating the values of the pixels in an image is something which is highly parallelizable, and it can be done faster if you have many computing cores. And so the number of computing cores in a GPU goes from a few hundreds. I have one in my laptop, for instance, and I think it has around 700 cores. And if you look into the very high-end GPUs, they can have very close to 20,000 computing cores. Now, a computing core of a GPU doesn't compare directly to a computing core of a CPU in the sense that they are, one by one, they are less powerful than a core of a typical CPU. But because their number can be very large, they in fact outperform all the CPUs, in fact. Another limitation of GPUs, at least of common GPUs, is also coming from the fact that they came from the graphics industry. It's a fact that when you want to generate an image for a computer game, you don't need a super high accuracy. So in fact, historically, the GPUs were optimized for single precision computations and much slower at double precision computations. I will show you the main features of a few types of GPUs that exist nowadays, and you will see that there is still a difference in performance, but now the gap is closing to some extent. Another limitation, at least if you look at the GPUs that existed like 10, 15 years ago, is that they were taking some shortcuts with the accuracy of certain functions. Like for instance, the square root was less accurate than what you will have on CPU, because again you didn't need all this accuracy to do graphics. But now recent generations of GPUs are totally compliant with common standards for floating point accuracy. So there are standards that define how many digits of accuracy should such and such function have, and they obey these standards in full. But I think the compiler has a flag to tell it that you don't want this accuracy, and it will generate a faster version of these functions for some of them. Another thing about GPUs is that most GPUs can have higher performance if you look, or if you use even reduced accuracy. So there is something. So I recall you that double precision means representing a floating point number with 64 bits. Single precision is with 32, and they have even smaller formats like 16-bit floating point format, which at least for some GPUs are even faster than single precision. Now, I've never tried that because if you work with half precision, 16-bit. For scientific applications, it's a little unclear whether it's enough. It might depend on the problem you look at. But this kind of reduced precision numbers are used a lot in machine learning, for instance, where to train a neural network, you don't need a lot of accuracy in computations, but you want it to go super fast. Because they take advantage of the speed. And then it's something I mentioned earlier, that GPU in principle wants to execute the same instruction, so in clock for clock, the same instruction in all threads. And you can't deviate from that, but then essentially it serializes all the instructions, which means you lose all the benefit of the parallelism. So here the sentence is a little too strong. The correct statement is that the instructions are scheduled for a group of 32 threads at a time, and these 32 threads must execute exactly the same instruction at all times. But this group of 32 threads does not need to execute the same instruction as the next group of 32 threads. So a practical slide. Let's assume you want to try this out at IPhT. So first of all, at IPhT, I believe some personal computers or laptops have GPUs that can be programmed with CUDA. We have another computer available on IPhT network. It's called Akira, and it has 2 GPUs in it, which allows to play with that and to even to do some reasonably sized calculations. And then for bigger projects, you can access, but that requires writing an application, the computing resources which are administered by agencies. So this is a national agency that overhauls all the computing resources for academic projects in France. And I've applied for computing time at Idris, and they have this nice thing in their application system, which is that for small projects, it's enough to write like a 2-page application, really. You send it by email, and you get an answer a couple of days later. And with this small project, they are trying to fill the holes available in the machine, and I believe most of them are accepted if it looks like it's science. But what they call small projects is actually pretty sizable. It's 50,000 GPU hours in a year. If you do the math, it's like having 4 GPUs for you 24 hours a day, all days during the year. So it's quite convenient. And the GPUs you get access to are quite a bit faster than those we have this machine, for instance. So this is a cartoon of what's inside a GPU if you were opening the package. It has computing cores, which have been represented by these purple squares, and it has memory, and it has another part of the circuit which is taking care of scheduling the task and so on. But compared to a normal CPU, there is a larger fraction of the area of the chip which is used for computing cores and much less for the logic. That's why the scheduling possibilities of the task are much more constrained than what you would have on a CPU. And then it has memory, And the memory is organized a little bit like in layers, like on a CPU. You have what is called global memory. This is the largest amount on a typical GPUs, sorry, that exist nowadays. This can go from a couple of gigabytes to almost 100 gigabytes for the very high-end GPUs. And then you have several levels of cache, the level 1 and level 2. And the level 1 is the fastest. It's actually on the same chip as the computing cores, which means that if the data is already in the level 1 cache, it can be accessed very quickly. And the level 2 is somehow intermediate. And the global memory, of course, is the slowest. It's a larger amount of memory, but it's the slowest. And the reason why it's called global is that this part of the memory of a GPU is visible both from the GPU and from the computer which is hosting the GPU. So you can write to this memory by issuing commands on the host computer or read data from this global memory. You cannot access the other levels of memory from the host computer.
Sorry.
Yes.
The group, I mean, the smallest subgroup has a type. Does it have a typical size?
Yes. So there are like it depends a lot on the model of GPU, but the typical number of cores on one of these sub-packages is a couple hundred cores. They are called, I think, symmetric multiprocessing units, SMU, I think. And the thing is that when you launch a calculation that will use many threads, this computation or these threads are grouped in what they call blocks. You can choose the size of a block, but what is guaranteed is that a block of threads is running on, all the threads in a block are running on one of these subunits. And they see the consequence of that is that they see a common L1 cache and they can communicate through it. While threads that belong to two different blocks may be on two different of these subunits, and they will not see the L1 cache. So therefore, the only way to communicate is by writing something in global memory and reading it out, which takes much longer. So to give you slightly more feeling about what numbers we're talking about. So the number of computing cores is, well, many, from a few hundreds to a few tens of thousands. The memory range is typically from 1 to 2 gigabytes to, I think the highest I found by looking on Google is 192 gigabytes. The L1 cache is on the same chip as the cores, so it is very fast and it's shared by all threads that belong to the same block of threads. The L2 level of cache is not on the same chip, therefore it's slower. And the number I found by Googling is that the latency, so the time it takes before, say, a thread wants some piece of data which is in the L2 cache, the number of clock cycles it takes for this data to be available is typically around of the order of 100 clock cycles. So it's rather slow. And then the global memory is also not on the chip. It's even slower. The typical latency now is around 500 clock cycles, but you have, of course, much larger amount of memory in this part. What these latencies mean is that, of course, the GPU is not waiting, without doing nothing while the data comes back. What the scheduler does is that at each clock cycle, it looks at what threads can run because the data they need is already there. And it will run those threads that have already their data. And at the same time, it will ask the data for the subsequent threads. So what you can already get out of this is that To make this work efficiently, and let's say you have 2,000 computing cores on the GPU, you should not just send a task with a couple hundred threads to the GPU, otherwise it will spend time waiting for the data. You should send 50,000 threads on the GPU so that the scheduler can always find threads that have their data already available and run them. This is a general optimization strategy. If you want to make it fast, you should use as many threads as possible, not just. Another thing I should mention is how a GPU is connected to the host computer. So it's connected by a rather fast connection that can transfer. These numbers are probably outdated. I believe nowadays the bandwidth between the host computer and the GPU could perhaps reach 1 terabyte per second. But nevertheless, it's fast, even if it's in this range. And there are, for systems that have more than one GPU, there are also sometimes direct connections between the GPUs, which means that if GPU1 needs a piece of data which is on GPU2, it can request it directly from GPU2 without going through the host computer. This makes the availability of this data a little faster. So this I already mentioned, that a GPU has devotes more hardware to computing and less to the scheduling and the control of tasks. So it means that it's designed primarily for executing common instructions in as many threads as possible. Something I didn't mention is that part of the L1 level of cache can be managed by through programming. So in fact, you can reconfigure a part of this cache as some kind of shared memory that you can explicitly write or read from. And this is used for communication between the threads that sit on the same of these subunits. And it's called shared memory. You cannot do that for the L2 cache. It's present on the GPU, but it's not something you can control yourself. So the hardware of the GPU is doing that under the scene. So now I will list a few types of GPUs that are commonly available these days. So this one probably is a little old nowadays. It's a one on my laptop. It has almost 900 cores, 4 gigabytes of memory, and the peak performance is in single precision is 2.5 teraflops, so 10 to the 12 instructions per second. And in double precision, it's only 81 gigaflops. So there is a ratio of 1/32. And this is one of those consumer-grade GPUs for which the processing power in double precision is really more than one order of magnitude below the processing power in single precision. So it's not very favorable to do double precision computations on this kind of GPU. Another thing I want to mention just for fun is the fact that when I started working here a long time ago, 2002, I had a discussion with somebody doing lattice QCD in Orsay, and this person was very excited at the time because he was going to receive for the first time a computer doing 1 teraflop. And at that time, 1 teraflop meant a computer that was taking a full cabinet from floor to ceiling of that size, and that probably used like 20 kilowatts of power. And now you see I have this amount of computing power on a laptop that uses 50 watts, which sits on my desk. So this one I mentioned it. So now the GPUs I'm going to mention as examples are those that I can use at Idris where I obtain computing time. That's why I look at the documentation. So this one has 5,000 cores, 32 gigabytes of memory, and the peak performance in a single precision is almost 16 teraflops. Well, I should say one thing about what they call peak performance in the documentation. As usual, it's very hard to reach this performance in genuine code you write yourself. It is a performance you can achieve if the data is always immediately available and you manage to have a sequence of instructions such that you really manage to do one operation per second without any stop. But nevertheless, they are fast. This is a slightly newer generation of GPUs. It has 7,000 computing cores, 80 gigabytes of memory, and now the peak performance is about 20 teraflops. One thing I didn't mention, which was also true of the previous one, is that the gap between single and double precision for those GPUs is only a factor of 2, not the factor of 32 for the GPU in my laptop. So these are, of course, not the same kind of GPUs. They are GPUs that are not meant for computer games. They are really meant as computing devices, and their price is not the same as well. So this is a so this will be the generation -2 compared to now. This is a previous generation, and this one is are the GPUs that will replace. They are not yet installed in the computer at Idris, but they will be installed in a few months or a year or so. So these are the current generation. And they have almost 17,000 cores, also 80 gigabytes of memory, and now the performance in single precision is approaching 70 teraflops. So these numbers perhaps do not mean so much, but I have another measure of how they perform, which actually matters a lot for the people who design and construct these supercomputers, and especially for those who pay the electricity bill in the end. It's the number of the power they need to run. So I took two of those, the generation -1 and the current generation. This one is requires 400 watts. And for 19.5 teraflops, so it's you could write the performance as 49 gigaflops per watt. The next generation will reach 96 gigaflops per watt. And here I've looked on Google what seems to be the highest performing CPU you can buy nowadays. It has 96 cores. It reaches 12.2 teraflops and needs 350 watts. So this is only 35 gigaflops per watt. So in a sense, by that measure, the GPUs outperform by a factor of 3 the best CPUs available. I didn't look extensively into that. Perhaps there are less powerful CPUs that have a more favorable count of gigaflops per watt. I'm not sure about that, but in terms of the power of computing power per electrical power needed, GPUs also have an advantage over CPUs. So now I should discuss a little bit what kind of tasks GPUs are good for and not so good for. So as I said a couple of times already, they are very good if your task involves doing exactly the same sequence of instructions on a large array filled with data. This is typically the things where GPUs will perform very well. I forgot to say something. And the successive threads in your program access successive entries in your array. If the threads access data in a big array but in a kind of random fashion, this will not be so good because the usage of the cache will be very poor mostly. So it's really good if you run 2000 threads accessing the 2000 successive entries in an array, for instance. This will work very well. If you access an array but you access only one entry every 100 entries in the array, it will not perform very well because the cache will not be very efficient. Another thing we will see in the little example I will show you later is that they work best if you have a lot of computations compared to the amount of memory you need to read. So they work quite well if the data is on the GPU, you copy data on the GPU at the beginning of your program, and then you do a lot of computations on this data, but the data stays on the GPU, and only at the end you retrieve the result from the GPU. If you have to do frequent copies back and forth from data on the GPU to the host and back to the GPU and so on, this will kill your performance by a large factor. So typical computation which works efficiently is that you have some data which usually will be produced on the host computer. You transfer this data in a single copy to the GPU. You process it on the GPU as much as you can, and when you're done, you copy back the result to the host. But you try to limit these copies. One thing that will not work well on a GPU is this: if you have code where each thread will execute a different sequence of instructions. So you have typical code is that you have lots of tests, if, then, so do something, otherwise do something else. So where the logic is making the threads branch in different directions. So this is called divergent code, and for this GPUs are not good at all. And as I said before, they are not so good if the pattern of memory access is also kind of random instead of being sequential. But you see also that this problem of having a sequential memory address is, or not having it, is also is something which is not always easy to achieve. If you think of an algorithm as simple as multiplying two matrices, the first matrix in the product will be read following the rows, but the second matrix will be read following the columns in the product. So if you've ordered your arrays in a certain way, following the rows will indeed correspond to sequential addresses in the array, but jumping from one column to the next will mean that you have a big jump in the array each time. So there are tricks to organize this kind of computation in a way to avoid the jumps. But if you code it in the most straightforward way, the pattern of memory access will not be very good to fulfill these constraints. So there are three main brands of GPUs. Intel is making some GPUs nowadays. The other one is AMD. And the one we're talking about here is NVIDIA. The reason why we will be restricted to this is that CUDA is in fact a software framework to program specifically the NVIDIA GPU. So in fact, it was designed by NVIDIA software engineers. So CUDA will not work on other brands of GPUs. So there is a way to know for a given computer what GPU or what NVIDIA GPUs it contains. The command is called NVIDIA SMI. So you open a terminal, you run this command. So I went on Akira, which is one of the computers at IPhT. If you run this command, you get this type of output. So this is telling you that it has two GPUs because you have these two lines. They are numbered 0 and 1. It tells you the type of GPU they have. It tells you how much memory they have. So here 12 gigabytes, and how much memory is currently used by the running processes. Also, it tells you how much power they are using right now. It's not so important. And you can see the list of the processes running on the GPU 0 and GPU 1. It's also possible that a single process is using both GPUs at the same time. It's not the case. So the goals of this course, as I already said, are twofold. The first one, and this is what is going to take me the longest in the series of course, is to learn how to write correct CUDA programs. So by correct means three things. They have to compile without errors, otherwise you don't have a program yet. They have to run until the end without errors. And they have to produce the expected output. So you must have, it's very useful if you have at least one case where you know what's the expected output to check whether it works. So the compilation without errors is rather easy in the sense that once you get used to the language, it's quite straightforward to write codes that compiles without mistakes. The second item to run without errors is probably the most problematic of the three, at least in the beginning, because it's rather complicated to, well, if the program crashes, it's also an easy case, so to speak, because you can very stop running. But if it runs and produces an unexpected answer, it's a little difficult to debug in the sense that the usual method of inserting print statements here and there in the program is it can be done, but it has some limitations, because if you if you do that in a function that will be called by 10,000 threads and you put a print there, you will have 10,000 lines of output, which is basically useless. And furthermore, because you don't control which thread runs first, they are out of order. So this output is not so useful unless you're more specific in what you print. And then the second goal is to try to optimize things so that they run faster. And it's something I already mentioned. You want to use as many threads as possible. And you want to try to think about how the memory is accessed, in which order, whether it's sequential or more random. And very often a large improvement can be reached in this way. So let me start by a little overview. Then we will do the break, and then after the break, I will discuss this very first example in detail. So CUDA is not the only programming framework to write code for a GPU. There are two more at least, and certainly others which are less well known. One is called OpenACC. ACC is the beginning of accelerators, and OpenACC is a little bit similar to OpenMP. So in fact, you start from a sequential code that has no parallelism in it, and you identify certain sections, certain loops typically that will gain from being parallelized. And you add tags before this loop to indicate to the compiler that this is a place where it will be beneficial to use what they call an accelerator, so a GPU in that case. But then it's up to the compiler to decide whether it will actually offload the computation of this loop on a GPU or just keep it on the CPU. So you have less control about what is really going on on the GPU. But it's more generic in the sense that, as far as I know, OpenACC works on any brand of GPUs. And the other benefit is that you can start writing a program that works but is not parallelized, and from there you try to make it faster by parallelizing certain sections. Another of these frameworks is called OpenCL. This I've never tried to use, so I don't really know what it looks like. So I took this from a very high-level description. It's a programming language which bears some resemblance with C and has some extra instructions to write programs that use GPUs. In principle, it's the programs you write in this language are portable across all brands of GPUs. But what this means is that they will run, but probably not optimally, in the sense that because it's more generic, it knows less about the specificities of the hardware it's running on, and therefore it's not optimized for a given hardware. And then you have CUDA. So CUDA is specific to GPUs made by NVIDIA. And it's a rather small set of instructions in C or C++ to run code on these GPUs. So it's not portable to other brands of GPU, but it's better optimized for NVIDIA GPUs because what's available in the software matches rather closely the features that exist on the hardware. So because of this close relationship between the software and the hardware, it runs quite fast on NVIDIA GPUs. So I'm mentioning that originally it's a set of extensions written in C and C++, but CUDA can be used also in other languages like Fortran. So there are wrappers around CUDA that allows you to use it in Fortran, in Python, and probably a few other languages as well. Most of my examples will be in C, but I will try to find a few examples also in Python to illustrate how it's done. What is CUDA? So CUDA it's not a programming language in the sense that it's an addition on top of C or C++. It's not a new language. So it uses the syntax of C++. Typically, the source files are called something .cu. Cu is the beginning of CUDA, but this is not mandatory. It's just if you inspect a folder, the content of a folder, you will recognize which are CUDA files and which are not by using this extension consistently, but it's not mandatory. But by having also always the same extension for all the CUDA files, you can write a make file that will automatically compile them in a single instruction, which is quite convenient. There is only one thing you have to pay attention on the surface. In fact, you could think of CUDA as being C, with one caveat, which is that if your source file is split across several files and one contains CUDA instructions plus some functions and the other is C, and you want to call these functions from the CUDA file within C, if you try to do it like that, it will not work. You have to decorate all the functions in your CUDA file, all the functions you wish to call from outside, to be more precise. You have to decorate them with this extra label, extern C. The reason for this is that a given function in C++ can actually be compiled into several distinct functions in the binary program, because the same function name can apply to variables of different types. And what's happening under the hood is that it's not that the running program recognizes, oh, this is a float, I should run it with float instructions. It's more like the compiler has generated the binary code for floats, for integers, or whatever. And depending on the arguments with which the function is called, is actually using one of these precompiled functions. So the function name in the binary is not the function name you think it is, it has been changed. And adding this here is following the naming conventions of C in the binary, so that your program in C can find. And then this is something I mentioned. You have wrappers to use CUDA from Fortran, from Python, and a few other languages. And one thing I didn't mention, I will talk about that in the last course as well, is that there are several situations where you don't have so much work to do because somebody else did the CUDA programming and wrote a library of useful functions. So for common tasks, this is already the case. For instance, you have a library for doing fast Fourier transforms in CUDA. You have a library for doing linear algebra in CUDA. So for those familiar with that, you have the implementation of the plus, what is it, basically linear algebra software, I think, for CUDA. You have a few other packages already written in CUDA that you can just reuse and not program yourself. And the advantage is that the ones I mentioned right now had been written by software engineers from NVIDIA. So in principle, they know what they are doing and they know very well the hardware, so it works fast. And if you were to implement it yourself, probably it will not work. So whenever you can, do not reinvent the wheel. Maybe we stop here for the break, and I will continue.
Okay, just we ask if there are some questions around in the room or in the virtual room. And for people in the virtual room, I just wanted to pinpoint that we will hear you if you just connect your microphone and ask questions. So there are questions?
Yes. So in the new GPU, now there is a distinction between the normal cores and the tensor cores.
Oh, yes.
Can you mention what is the difference between the two?
The tensor cores are a part of the circuitry that optimizes the multiplication of a small matrix, typically 4 by 4, by a vector is for increase plus another vector. So they do, let's call this A, this is X, and this is B. So they compute AX plus B, and they do that with reduced, one of those reduced precision formats. They can do that for various formats, but most of them have less precision than simple precision. So that, like 16-bit floats, for instance. I've never used that feature myself. I know they are very useful for all things related to machine learning. For general purpose computing, perhaps not so much because of the reduced precision they force on you. But I've not read them, but I've come across some articles explaining how to do general purpose linear algebra using these tensor cores. So some people have thought about it, but it's a little tricky in the sense that you have to do most of the calculations using this reduced precision, and then there is a final step to restore the accuracy you desire, which have to use the other cores.
In your code, you can choose to which one you send. So
yes, but no, by default, it's going to the normal computing cores. There are a set of instructions to directly do computations on these tensor cores, but I looked a bit briefly through the documentation, and I didn't spend the time and the effort to learn how to use it. Okay. But they are accessible to, how to say, to a person writing his own programs. You don't have to go through a specialized library to use it.
Because I know for machine learning it really helped. I mean, I could see the speed up, but how it works, I never understood.
So here it's really a special part of the hardware which is devoted to this very, very specific computation, and the circuits are such or simplified so that they handle only these reduced accuracy formats, which makes them much faster than doing the same computation on the regular cores.
More questions?
Yes.
What you mentioned about a little bit the restriction on the sequential preference regarding the threads,
Yes.
does it impose a restriction on the loading of threads once some of them have finished before waiting for the others?
Threads will always run in blocks of 32. So if suppose you have a computation that will normally require only 33 threads. So it will use in full one of these blocks of 32, and then it will nevertheless need a second block, out of which 31 threads will be wasted, so to speak, and not used.
So, and also if 31 of those threads are very quick and one is slow, it will always have to wait for the last one.
Oh, this is, of course, yes, this is always the case, and it's worse than that, because if 31 are quick and the 32nd is slow, it certainly means they are not doing the same thing. So in fact, it will revert to sequential. So it will first run the 31 threads that are executing common instructions, and then those 31 threads will pause, and then it will run the last thread, with its own set of instructions. And then the function, this parallel function, will only exit after all 32 threads have finished everything. There is no exit until some of the threads are still working.
More questions?
We're going to see it later, but so the compilers via the wrapper, yes. Then you guys
explain on a simple example. But to answer your question in a very short way, there is a wrapper which is called NVCC, and I think it's just a shell script which under the hood calls the genuine compiler for the CUDA code and calls either GCC or some other compiler for the files which are not CUDA code. But it's transparent for you. If the compilers have been correctly installed, you just run NVCC and it knows where to find the headers, the libraries. You don't need to specify the Python.
Even if you write Python code inside, it will.
This I've never tried. So I should sit down and figure it out for myself to show a few examples in Python. This I don't know.
How much are we talking about in difference in performance between the CUDA and the other options like NCL and ESS?
Probably not a factor of 2, but perhaps like 30% or something like that. But this figure probably varies a lot with the specifics of the code you're trying to run. CUDA, in a sense, forces on the software implementation, forces the software to follow rather strictly what's possible in the hardware. That's why it performs well most of the time. As the other languages for GPU programming being more generic, they don't force these assumptions about the hardware, so you could write codes that in a sense is poor match for the available hardware. But nevertheless, probably code written in these other frameworks will nevertheless work faster than ordinary CPU.
It's okay. Yeah.
Okay. So yes, I stopped at this slide before the break. So now I will go a little more into what's available in the CUDA language. And there are several types of functions available in this extension, Express. First of all, you have all standard functions that you will find normally in the mathematical library of the C language, so sine, cosine, whatever. There are many of them, both in single and double precision. So they have the same names as their counterpart in normal C or normal C++, so the sine is called sine. And the only thing is that depending on the context, so typically what kind of function it appears into, the compiler will determine whether it needs to produce the binary function for the CPU or the binary function for the GPU. Okay, you don't have to tell by hand which function you need to the compiler. There is a way to do that. For instance, you can decorate a function with a certain type, with certain tags that will instruct the compiler to produce the two versions of the function, one for the CPU and the same function with the same name for the GPU. So this is for your own functions. But otherwise, you don't really need to specify. Then there is a whole family of functions that are used to transfer data from the host to the GPU, from the GPU to the host, to allocate memory on the GPU, to deallocate memory on the GPU, or also to copy directly from one GPU to another GPU. So they are, if you are familiar with this, they are the analog of the functions malloc and memcopy, you can see. So we will discuss that in detail later course. There are, of course, functions that will start a parallel computation on the GPU. So you instruct the GPU to do a certain parallel computation. And then another family of functions are those that can be used to control the scheduling between tasks. So this is something I will talk about, I think 2 weeks from now. You can have, of course, several tasks. So you could do this computation, transfer this data, do another computation. And by default, they are piled up in a queue of tasks to be done, and every of these instructions will be done one after the other. This is a default. And then, if you want to deviate from this default, for instance, you have a certain subset of tasks that depend on one another, so it makes sense to put them in the same queue. And then you have another subset of tasks which are independent of those of the first set, but dependent among themselves. So what you would like to do in this case is to create a second queue, which is independent of the first one, where you put in the second queue all the tasks which are independent of the first ones. And then you have two independent queues of tasks. But then once in a while, you need to start a task from the first queue only after another task of the second queue has completed, for instance. And you need a way to signal when this completion is active. So this is part of these functions that help controlling the scheduling between tasks. So the main steps of a typical computation on a GPU could be the following 4 steps. First of all, you have to reserve some space in the memory of the GPU for the data you're going to use. You have to populate this space with useful data. This can be done in 2 ways. One way is to compute this data on the host computer and then copy it to the GPU, or another way is to calculate it directly on the GPU, if that is possible. Then, once you have this data on the GPU, you usually want to do 1 or more computations using this data on the GPU, and the more computations you do with the same data, the better. And then these computations will produce some output which will be stored on the GPU, and you want to retrieve the result on the host, either to further process it or to print in a file or whatever. So this is always pretty much the same sequence of steps. So now I will go through one very little example. So first of all, I will explain this example, what it does and what are the main steps this is a CPU version of this little program. It's a program that does nothing useful. It's just for testing. So let me explain what it does. You create 2 arrays, A and B, large arrays. They have 256 million floating point numbers in them. And then these 2 arrays, you populate them with random data. These are numbers between 0 and 1, just to have some data in them. And then you apply a certain function. So you take the number A of I, B of I, you apply a certain function which is defined here that takes 2 arguments and returns 1 number, and you put it back in A, and you repeat this 256 times. This is just a dummy computation, just meant to be long enough that I can measure something, and the function is itself a silly function whose only purpose is to have be non-trivial to calculate, if you want. And the only thing I've done to do a fair comparison on my laptop is that I've parallelized this loop. This is a main loop that goes through all the cells of the array. I'm parallelizing this loop using OpenMP with 6 threads, because my laptop has the CPU of my laptop has 6 cores. Okay, so this is the best I can do. So it's a very simple program. So now I will show you the GPU analog of this program. So the first thing you see is that I have to include two headers which are specific to CUDA. These are the headers you have to include all the time if you have a file with CUDA instructions, because these headers contain the definition of all yes.
Sorry, I don't know if it's possible, but if you can zoom in a little bit.
I'm afraid not, unless you.
There is some. No, it's okay.
Not. In fact, it's my fault. I reduce the font. I reduce the font so that all the listing fits on the screen. So I'm pretty sure if you come a little forward, you can see it. So while he's searching a way to improve this, I have to tell you, I will make these source programs available on the website of the course, along with the make files that can compile them without mistakes. So this way you can read them carefully and modify them to play with them. Going back here, the first two lines are just the inclusion of the headers that contain the definitions of all CUDA-related functions. The second thing notable is this function. You see it's almost exactly, in fact, it is exactly the same as the function here. The only thing I've added is this decoration in blue here that says device between underscores. And this is telling the compiler that what I want is the version of this function that runs on the GPU, not on the CPU. I will comment a bit more on that later. And then the second, and this is new, the second thing you see here is something that looks like a kind of the kind of function that takes two arrays A and B, and it applies a function f to A and B and put it back in A. And the global between underscores is indicating that this is a function that runs in parallel and is called from the host computer. So while the first one, the function f, runs on the GPU and is called from the GPU. And I will explain how the index ID is calculated here, because this is very specific to CUDA. So for the time being, just accept that this is a proper syntax. Then the first two steps inside the main function are the same as before. I allocate two arrays and I populate them with random numbers. Here you see something additional. I'm defining two pointers, so this will be the addresses of the arrays on the GPU, and at least this is what I'm doing, but it's a common practice. I think it's to have some kind of modification in the notation to know just by looking at the name of the pointer whether it's a pointer that relates to something on the device or on the host computer. So this D underscore is my way to remember that these will be pointers mapping to data on the GPU, on the device. Okay. Otherwise, it can be a little messy, because in your program you will have pointers or array names of arrays that live on the host, on the GPU, and after a few days you don't recall which one is which, and it's it's messy. So what I'm doing here is that I just declare two pointers, and then the next thing I do is that I allocate space for these two arrays on the GPU, and they have exactly the same size as here. So the function that does that is not called malloc, but CUDA malloc. So you will see very quickly that all functions that are from the CUDA library, their name starts with CUDA something. I think all of them. So here you just say reserve n times the size of a float and put it at this address, or rather tell me the address in this variable, and the same for the second one. The next two instructions will copy this random data I've calculated on the host, and they will copy it to these arrays that live on the GPU. So here it says copy, it's the same syntax as memcopy in C. So the destination is the first, the source is the second, the size you want to copy. And then there is a last flag which is not present in the normal memcopy function, which tells whether you want to copy from the host to the device, to the GPU, or from the GPU to the host, or from the GPU to another GPU. All possibilities exist. So this one is host to device. The name is pretty explicit. And it's a mistake to have host to device and this be a device pointer and that a host pointer. So if you mess up with the order of the pointers, probably the compiler will complain, otherwise it will crash. I'm not sure exactly. And I think with recent versions of CUDA, the compiler is smart enough that you can omit this, so it knows from the pointers you put here which direction you want to copy. So you have to check for the documentation if you want to use this. Otherwise, it's not hard to add it. So at this stage, the random data I've created on the host here has been copied to these two arrays on the GPU. And then I will do repeat time, so 256 times. I will call this, which is applying this function. So this is a syntax for applying the function f to all entries in the arrays. And then I think this is unnecessary, but I've put it here to mention the existence of this function. CUDA, the function CUDA device synchronize without any arguments will just pause there until all queued computations on the GPU have been finished. Because one thing I should mention is that this call here it's a call to run in parallel on the GPU. It will return to the host before being completed. So it will just queue 256 of these calls and return immediately, probably before they are finished. So this function here, CUDA device synchronize, is a breakpoint where the execution of the program will pause until everything that has been queued on the GPU until that point is finished. Okay, and then the last instruction is to copy back the result of this array which is living on the GPU to the array A on the host. And now you see the order has changed because now it's device to host as the order of the copy. And then it's finished. So yes, this is something I explained already. You have to put systematically in at the beginning of your files that contain CUDA instructions these two headers. If you're going to use functions from additional library like for the fast Fourier transform, for instance, I guess you need additional headers that define these functions from the Fourier transform library. But at least the ones you need all the time are these two. So now this, I explain what the device means. So it's just a decoration of a function. If you don't look at this tag, it's really the normal syntax for declaring a function that takes two floats and produces one float as output. The device before the function name tells the compiler that what you want is a function that will run on the GPU and is called from the GPU as well. So the compilers know that it has to produce a proper binary instructions for the GPU. Besides a device, you have another possibility, which is host, which will produce the function that runs on the host computer. You don't need to put that explicitly, the host, because this is a default if you don't put anything. And then you could have both at the same time, device host before the function name. And this will tell the compiler that you want both. You want a function named f in this case, and you want the two functions, the two versions of the binary. You want the binary that will execute on the host and the binary that will execute on the GPU. This saves you a little bit of writing because you write the definition of the function only once, and this limits the risks of making a mistake by writing it twice. And if you want to change later what the function does, you don't need to change it twice, you change it only once.
Are there any restrictions on the functions that you can define on the device?
Pretty much any function you could define on the host in C, you can take it and it will compile on the device as well. I think the CUDA libraries, they implement all the existing functions of the standard C library, the mathematical functions. Include things like Bessel functions, J0, for instance, is present. I've seen. Perhaps there are a couple of exceptions, but I'm not sure. I've never encountered one that would compile on the host and fail to compile.
Also for double.
And then all these functions exist in double precision as well. With the caveats I mentioned that double precision computations run slower. Yes.
About a function that is supposed to run on the device, in the definition, I can also loops and other things.
Yes, you can have loops. Here it's a function that is just a combination of elementary functions, but you could have a more complicated calculation of these functions that includes loops. All the standard C syntax works in CUDA. Loops.
And tests.
You can have tests, yes. Now with the caveat that if your function has a test, it means that the computation of that function can take at least 2 branches. And that using this function inside of a parallel code might make the code divergent because all threads will not follow the same instructions. So one will have to be a little. It will work, but perhaps slower than you expect if you have tests. And then the tag global in front of the second type of function indicates, so the jargon for this is it's a CUDA kernel, and it's a kind of special function which is called from the host. It will execute on the GPU, and it will execute in parallel in a large number of threads typically. And in the syntax, the syntax to call it will come later. It's not on this slide. So the only thing to remember is that these tags here, these 2 tags, or the combination of both, define functions that execute on the host or on the GPU, depending on which tag you use. And global always indicates a function which executes on the GPU and is called from the host, and will run in parallel in a large number of threads. In fact, it will run in parallel in one thread if you instruct it to do so, but there is no point in doing that. So I'm going through the the memory management functions that appeared in my example. The first one is CUDA malloc. It works almost in the same way as the usual malloc in C. The difference is that you first declare the pointer. I didn't reproduce the declaration of the pointer D sub A before. And then, the normal malloc doesn't have this first argument. It's you get the address as the output of the malloc function. While here, you pass the address of the pointer to the function, and the function will write the address into the pointer. The rest is the same. You tell the function what the size you want to reserve in memory. So here, n times the size of the float. And then you have all the functions of the CUDA memcopy family. Here it's just one function, but there are several others. So where you tell the destination, the second argument is the source, the pointer to the source, then the size of the area in memory you want to copy. Just one restriction, it's the same as memcopy. You can copy only contiguous zone in memory. You cannot make a copy that has jumps. There is a function for doing that, but it's not this one. And then the last argument is telling the function the direction in which you want to copy. So you can see all the alternatives. You have host to host, device to host, device to device. And the one I was mentioning before, if you put CUDA memcopy default, it means the compiler will try to figure out what you mean from the definition of the pointers. So in principle, the compiler has enough context to determine if a given pointer lives on the host or lives on the GPU, because you didn't reserve the corresponding memory in the same way. And therefore, the compiler, in principle, knows where the corresponding memory is located. Of course, if you forgot to reserve the area in memory, you're out of luck, because the compiler will not be able to determine where this memory is. But if you forgot to do that, you have other problems to begin with. So in principle, you could use this all the time. This might work. Otherwise, it's not hard to put explicitly which one you need.
Question: do you need to free the memory once used?
I never do it. No, I never do it because the kind of programming pattern I use is that I allocate all the data I need at the beginning of the execution of the program, and this data, the storage lives until the end of the program, and when the program terminates, it's automatically free. Now, there are situations where you could have a point in allocating a certain amount of data at every iteration of a loop. Okay, so but not gigabytes, of course, so just little chunks, iteration of a loop. And unless you know exactly what you're doing, the risk is that this is going to be out of hand very quickly. So allocations you do within a loop, in general, you will better take care of freeing them as soon as possible, because if you run this loop again, you will run out of memory very soon. So
how do you free it?
It's called CUDA. I will write the syntax. So suppose you want to free the memory that was allocated with the first CUDA malloc. I believe you will do CUDA free. Yes, it's just DA. It's this.
Okay, thank you.
I will explain that when I discuss in more detail all the memory management functions, I guess, next week. So yeah, in principle, you will better be careful and freeze the data you don't use anymore, unless you know the amount of data you need is fixed once for all. Okay, so now I come to this very important feature of CUDA, which is really specific to CUDA. It has no counterpart in C. It's how you call one of these functions which is meant to be run in parallel. So it's called the kernel in the CUDA jargon. And the syntax, is a bit peculiar. So it's here. It's a name of the kernel, so the name with which it was defined. Then you have this triple symbol, the smaller symbol 3 times. You have 2 numbers that I will explain, and then the closing, the 3 times the greater symbol. And then you have a bunch of arguments which are passed to this function. Perhaps it's useful to go back to the definition here. You see this one was taking 2 arrays A and B. So you have to call it with matching arguments. Of course. The compiler will check that you call it with the appropriate arguments. So here the pointers to the 2 arrays, and they have to be arrays that live on the GPU. If they are arrays, calling a function that executes on the GPU with pointers that point to data that lives on the host will probably not work. So now I should explain what's the syntax here. So when you call this function to be executed in parallel in a certain number of threads, you have to tell it how many threads you want. If you want 32 threads or 1 million threads, there must be a way to let it know. And it's done via these 2 arguments. So here, what it means is that, well, in fact, what I wanted in this example is to have n threads. N was 256 million. And what I'm telling here is that I want these threads to be divided into blocks of 128 threads. And of course, if I want n threads in total, there will be n divided by 128 blocks. Okay, this is just that. So the product of these 2 numbers is telling you what's the total number of threads you will have. So here, 256 million. So you see already that we're not talking about the same number of threads where you're used to if you use OpenMP. In OpenMP, typically you will try to have as many threads as you have computing cores. So if you have a CPU with 8 cores, you will parallelize a loop with 8 threads in general. While here, I'm calling this function with 200 million threads. The size of there are certain constraints on the size of the block because it has to fit on one of these subunits I was describing at the beginning. So that gives you what's the maximum size, what's the maximum number of threads in a block. I will try to find what this maximum is for the next course. But 128 is well within what's allowed. And another thing which is something to keep in mind is the fact that the threads will going to be grouped by packets of 32. This is at the hardware level, because that's how the scheduling of the instructions is done. So it doesn't make sense to have a block size which is not a multiple of 32. Because it means that in the last of these packets, you will have less than 32 threads. It will work, but it will work suboptimally because some of the threads will be doing nothing. So the block size is almost always taken to be a multiple of 32, and then the number of blocks is just the total number of threads you want divided by the size of the block. And again, you have to be a little careful in case n, the number of threads you want, is not an exact multiple of the block size. You have to do a little calculation in your head. You have to add the remaining. You have to add one more block, even if it's not going to be used in full. So to avoid this kind of silly mistakes, the suggestion I will give you is to have a block size which is always a multiple of 32, and have a number of threads which is always a multiple of the block size. And then all divisions are just exact integer divisions, and you don't have to worry about the remainder. A very important thing about these kernels, these parallel functions, is that they return to the host before being completed. This is something to keep in the back of your mind, because it doesn't mean that because they have returned, the result of applying the function is available for you. It's still in the process of being calculated. It's not a big issue in practice, because if you call this kernel and then immediately after you have a function to copy the result back to the host, it will work, because the function to copy the result back to the host will not start until the completion of the computation done by the first one. So there is no risk, at least in this simple situation, to try to copy back the data before it has finished being calculated. It's useful to keep in mind that it returns to the host before it's completed on the GPU. If you have successive calls to the kernels of this kind, they will be executed. So each of them is running many threads, but each of these kernels will be executed in sequence. So the second kernel will start only after the first one has completed. Even so, the first one is not using all the available computing cores. Another thing I didn't mention, because it was not a feature that I needed here, if some of the arguments when calling the kernel are scalar arguments, like just a number, these you don't need to pre-copy them to the GPU. They will be copied on the fly when you call the kernel. It's really very much like when you call a function in C, the small arguments, so like numbers, they are just passed by value to the function you're calling. And the larger arguments, like arrays, what you pass is the address of the array to the function. The address is passed by value to the function. You don't copy the entire content of the array to the function, of course. So it's really the same here. And now, but arrays, the content of these arrays DA and DB must already be present on the GPU when you call this function, because otherwise you will have garbage. Yes?
Sorry, maybe you already said it, but can you explain why did you choose this number of blocks?
Oh, the number of blocks is, there are several considerations that go into that, but mostly, at least at my level of understanding, it's mostly a trial and error. In a sense, what you want is to have, if you have blocks that are too large and they don't fit on one of these subunits, it will just not run. It will just be stuck there. So you want and perhaps the compiler will know about that and will not even compile your program. But except for that, if you choose blocks that are too small, so smaller than 32 doesn't make much sense because the smallest size of a pool of threads that will run together is 32. And then there is everything in between 32 to the maximal allowed size. And there it's a process of trial and error. It's more like an optimization process. There is a certain value of the block size that will make your code slightly faster than with users. But it's a bit hard to tell in advance. That depends a bit on the specificities of the code, because all the threads in a block, they run on one of these subunits. They share all the available resources of this subunit. So if your kernel is doing a rather complicated calculation, it needs a lot of registers, hardware registers to store intermediate results. And there is a finite amount of these registers available. If you have a big block that has many threads, it will not work so well because the number of registers available for each of these threads will be limited. But there is not one clear-cut answer valid for all situations to your question. It depends a little bit on what this function is doing. If it's doing something simple enough that doesn't require many registers to store intermediate results, I will tend to make the block size larger. That will probably perform slightly better. And then the important part in the definition of this kernel is, now I want to explain, no, sorry, it's here. I want to explain the calculation of the index, which is done here, because you see this variable ID is an integer which is used directly as an index into the arrays. So I want to explain what's the meaning of this variable. So block IDX, be careful, there is a capital I here, dot X is it's an integer that enumerates the blocks from 0 to n to the number of blocks minus 1. Okay, so here the number of blocks is this number, n divided by 128. And then since within a block, in my example, there are 128 threads, thread idx.x is a number that enumerates the threads within a block. So it's a number that goes from 0 to 127 in this particular situation. And then there is a third number which appears in the calculation of this index. It's block dim.x, which is the size of a block, so 128 in this case. It's this number here. And you see that now it's like the usual calculation of an index, which is represented by a certain block number and a certain thread number within the block. It's obtained by multiplying the index of the block by the size of a block plus the index of the thread within the last block. Okay, and that gives you the absolute index that you can use into the array. And now there is this dot X that appears everywhere. It's because CUDA, so here it means that I should make a picture perhaps to illustrate the point. And I will come back on that probably next time. So here you have a certain number of threads. You have n threads. The first index is 0 and the last is n minus 1. And then what we do here is that we group the threads in blocks of 128. So this one is 127. The second block has indices 128 to 255 and so on. So this is the block 0, this one is the block 1 and so on. The last one is here. So it's you view the threads are indexed by one number, like 9, and you subdivide the threads or the set of threads in blocks, and from the block number, the size of a block, and the index of the thread in its block, you know what's the absolute index of the thread. But so this is a one-dimensional organization of the threads. And because CUDA comes from the world of image processing, the language offers you the possibility to arrange the threads in a two-dimensional grid rather than a one-dimensional grid I did here. And it means, in fact, it can go up to three-dimensional. So to specify how the threads are organized in the other dimensions, you have to replace the dot x by dot y or dot z to access the second and the third dimension. I've never used this possibility in my own programs, but I could imagine this is something which is handy if you have, for instance, a three-dimensional volume that you want divided into sub-volumes, and you want to map each cell in this volume to a particular CUDA thread, and therefore a three-dimensional organization as opposed to one-dimensional would be much more natural. But it's the same, you have threads, you divide each dimension into blocks, and the sizes of the blocks do not have to be the same in all directions. And one last thing I already mentioned is that all threads that belong to the same block, they run on the same hardware chip. So the subunits are really the same chip. They see the same cache, and therefore they can communicate.
Sorry, the syntax, so if you use two-dimensional or three-dimensional geometry, the syntax of the call changes. The function call.
No, it means that these variables are no longer integers, they are arrays of three integers.
Okay.
I will explain the syntax
for
that next time. So this I already mentioned, it's to synchronize everything, so it means the host will wait until all the queued CUDA functions or whatever have been terminated. But this is kind of the brute force scheduling. It will just freeze everything until everything has finished on the GPU. And there are more fine-grained ways of waiting for the completions of just a subset of the CUDA tasks you started, but you don't care about the others. So this I will explain how to do it. This is a compilation. It's very important, but rather simple. The compiler is called NVCC. It's not actually a compiler. It's more like a script that will, under the hood, call the compiler for you. It has almost the same syntax as the GCC compiler. You tell it which file you want to compile, which output file, what's the name of the output file, the libraries you need to link it with. So you always need these three libraries plus perhaps a few others depending on your code. These are optimization flags. And that's all. Of course, it has many more options, but for a basic compilation, you just need this. And if it has been properly installed, you don't need to specify by hand where the CUDA libraries are located. The compiler knows if it's installed properly. So let me give you a flavor of the kind of speed up you can expect. So this was done on my laptop. The CPU has 6 cores, and then it has this little GPU, which is not very powerful. So this is the timing of the program I just described. So on the host CPU, it was taking around a minute, 63 seconds. On the GPU, it took 5.2 seconds. So here I measured only the time for the computation itself, not the time to prepare this random data at the start, because it's common to both. So you see that it's about 12 times faster. It's in single precision. If it had been in double precision, the gain would have been almost nothing, probably. One thing you see here is that there are some overheads for the allocation on the GPU, for the copy from host to GPU, or the copy from GPU to host at the end. They add up to about a bit more than half a second out of the total. So these overheads are not the computation itself, but they are there. You cannot avoid them. And this is why you should always try to maximize the amount of computations compared to all the rest, all the memory copies and so on. You see easily that since each memory copy takes about 0.17 seconds, if you do it 10 times, it's 1.7 seconds, which are gone in this example. There is just one example, one improvement I want to discuss. If you remember what I did I will show you again. What I did in this example is that I'm calling this function that runs on the GPU 256 times. So I've put the loop outside of the calls of this function. So there are 256 calls to this function. Of course, in this example, there is one naive change, which is to put this loop inside the parallel function. So now I'm putting this loop directly inside the parallel function here. And when I call it only once. And the computing time goes from 4.6 seconds to 1.4 seconds. So there is another overhead, which is just the time it takes to start one of these parallel functions. And from the comparison of the two timings, you can estimate that each kernel call has an overhead around 10 milliseconds, even if the kernel does nothing. So this is another hint that you should try to reduce the number of kernel calls and have kernels that do more work if you can. Because that will eliminate these trivial overheads. Perhaps I will stop here. I had two more iterations on this little example, but I've already exhausted the time. The thing I want to show you on the next slide, but that I will do next week, is how to, assuming you have two GPUs, how to split this computation on two GPUs that will do half of the computation each. This is very easy, as you will see. And then I will continue with the rest of my intended program. Thank you.
So, questions are welcome. Please.
Would it be with a test like the one that you made there, the way to know, like to know whether it's most beneficial to use OpenMP or GPU? So like, for example, if you have a more complicated loop structure.
Yes, so here it's clear. My example on the CPU was using OpenMP, but only on 6 cores, because that's what I have on my laptop. And this is the exact same computation performed on the GPU, and it was 12 times faster. So this is a clear-cut case where OpenMP underperforms compared to this GPU. Of course, it's not always like that. If I had a CPU, a more powerful CPU on my laptop, it might actually be faster than with a GPU. Because my laptop is 4 or 5 years old now, and the CPU is not very powerful because it's a laptop. So the situation is not always so clear cut. I believe most of the time, for the type of computation done in this example, where you just brute force apply a function sequentially to the elements of an array, the GPU will almost always be faster than a CPU. If your code has some more complicated logic with different branches being followed depending on the results of some test, it might not be so clear cut.
But it would be, from what you say, always connected to the branching of the program rather than
if branching occurs within these subsets of 32 threads, this is very bad because it will force the computation to go back sequential, even on the GPU.
But if it's just a linear algebra, very heavy, but linear algebra.
Super good. It's indeed super good for anything like linear algebra. Multiplying a matrix by a vector with something that will be very fast on the GPU typically.
In a GPU, does the number of threads depend on the complexity of the computation you have to do?
No, you decide the number of threads. So you could, and it's your choice really. You could decide to have less threads, and each thread does more work, or you could have one thread per tiny bit of computation. This is what I do here. You see, I have. Let me go back here. I'm calling this function with the number of threads equals to the length of the array. So it means every thread will only process one cell of the array. You could have a different organization where you decide that every thread is going to process 1,000 cells of the array and then have 1,000 less threads. So, except that 1,000 is probably not good choice because the original number of cells is not a multiple of 1,000, so you would take 1,000. It will make the logic of your code a tiny bit more complicated, not much. It's very often the case that when we have to do an operation repeatedly on the entries on an array, we just choose one thread per entry of the array. Makes the coding super simple.
Whatever this number, no. So it cannot be too much in a way.
No, there is no limit on the. No, okay, I should withdraw that. There is probably a limit that I've never reached. But it's super high in the sense that even if the number of computing cores in the GPU is less than the number of threads you ask, it certainly is in the case of my example, the GPU will just queue the threads until they have all finished. So in a sense, it's partially sequential if you have more threads. You don't have to care about that yourself. Handling that under the hood.
Sorry, could you restate again what happens if you do not use a CUDA device synchronize?
Here probably nothing, because so these calls return immediately, but the CUDA M copy, which is at the end, will have to wait until they have all finished, because it's you should think of this as a kind of queue where this is time. The first one that will be executed is the first CUDA copy here. Then the second one that will be executed will be the second CUDA copy. Then you will have all of them 256 times this apply function. Sorry, apply and then a final CUDA main copy. And within this pipeline, they have to be sequential. So this one will start only after this one has finished. The first instance of apply function will start only after this CUDA main copy has finished, and so on. So in fact, the final CUDA main copy cannot start before apply function has been done 256 times. So there is no risk of copying data which has not yet been calculated in full. So here you could remove it and the behavior of the program will be the same.
And so in general, in which cases you want it?
In which cases you want to, I would say it's mostly used for debugging purposes. Your program doesn't work, you don't know why. You put CUDA device synchronize after every call, and if it works now, you realize, oh, I have a synchronization issue. But indeed, I'm not sure there are really cases where forgetting it will lead to incorrect results. Now there are, I should say perhaps right away, there are asynchronous versions of these functions that return immediately, and with those there is a risk of trying to use the data before it's actually copied. So there are two risks with the asynchronous functions. The first risk, in fact, is that the asynchronous version of this function returns to the host before the data has been copied, and there could be a risk that you modify the source array before it has been copied, which of course is not something you want to do. So with these asynchronous versions of these functions, one has to be more careful. Yes.
So I guess in this example, I mean, you have some improvement because some static data, and I guess that's the purpose.
The data was created before here, and then but the data is changed every time you apply this function, because you see you apply f to a and b, you put it back on a, so it's not static in the sense that it's the same data at every iteration. Data is changing after each iteration of this function.
Conceptually, the 4 is precisely the, so if you have an application where you can do 4, then this is perfect for CUDA.
It works perfectly if you have a loop with a large number of iterations, and each iteration is independent of the other iterations. If you have a carry dependency as the loop progresses, for instance, you want to compute the running sum of an array, so the sum of the first p elements of the array, with p from 0 to the size of the array. Writing that in CUDA in a way that performs efficiently is much more tricky, because you have a dependency on successive iterations.
Like a Fibonacci.
Yeah, Fibonacci probably tricky, and of course will be tricky because it very soon produces huge numbers. Yeah, now this kind of thing might be tricky because it's more recursive than iterative.
Yeah.
Other questions? Okay, so if not, thank you, François, again.